In the previous video, we discussed the basic shape of sine and cosine, and next I wanted to discuss what happens when we want to change that. Let's say we were to apply a transformation to the trigonometric function. Say we took that sine wave and moved it up or down, left or right, vertical or horizontal translations as we define them in chapter 2, or we were to stretch them out, stretch them horizontally or shrink, compress them horizontally, or stretch them vertically or horizontally as well. What does all that look like, and how do we do that? And returning back to all those same ideas from chapter 2, everything works exactly the same. And I mentioned that at the time transformations will apply to any function. So it's just in trigonometry they all are given special names, and that's kind of what I wanted to discuss. So the amplitude is often what we refer to as the vertical stretch factor. So if you recall, let me pull out my pen here, is that when you multiply, say you're going to take 2, like x squared, and multiply by 2, that results in a vertical stretch by 2. And it had to do with whether it was on the inside or outside. So instead of reviewing all that right now, let's just kind of discuss what happens in the form of trigonometry, but it's all the same reasoning that we went into before. But basically, if you say you had 3 times the cosine of x, that will be a vertical stretch by 3. And instead of having an amplitude of 1, meaning that it just went up to 1 and came back down as it did before, it's going to actually be a lot taller. It's going to have an amplitude of 3. An amplitude is just what we call it. It's a very common name with wave functions for this property. And the amplitude is always defined to be a positive value because it's like a physical distance. And note that it's not the height of the entire wave. It's always half the height of the wave, because what a trigonometric function does, like with cosine, it starts at 0, goes up, comes back down, and goes below. But the amplitude is like the height of half of the wave. So if you're looking at the wave and you're trying to figure out the amplitude, just figure out the net height of the total wave and cut it in half. It's always the height from equilibrium to the top, not from bottom to top. And it should be the same in both directions because it's based off of a circle. Now, when you move the multiplier from the outside to the inside, as we know, that's no longer a vertical transformation but a horizontal transformation. Sorry, not transformation, stretch. But it's still a transformation, but it's more specifically a stretch or compression when it's on the inside. So say, for example, I was to do the cosine of 3x or the cosine of 2x. That would, instead of being a vertical stretch, it would be a horizontal compression. And recall that on the inside, it does the opposite sort of effect than what it would do when it's on the outside. As we got into, that's kind of the hard thing to remember because it's conceptually backwards. But one thing that makes it a little bit easier, and this is something I suggest memorizing, is that the period of a general trigonometric function is always its baseline period divided by the multiplier on the inside. And if you look at the packet and the little table of information, that's exactly what it says. The amplitude is baseline A, the number on the outside, and the period is always affected by the number on the inside. And it's not just that number, it's always 2 pi divided by the number. And when we look at some examples, we can talk more about why. And the other term, equilibrium, which I mentioned, is always the center point. But the baseline sine and cosine started at 0, or sorry, sine started at 0, cosine started at 1. But since it went from the max down to the middle and back to the max, 0 is the natural equilibrium for both sine and cosine, the middle of the wave. Now, obviously, if we were to add a number to it, let me go back to my graph and use that because it's a little bit easier to work with from the packet. The equilibrium was always the point, in this case, the x-axis, the part right in the middle of the wave. But if we were to say add 2 on the outside, we know that, well, that's a vertical transformation, say cosine x plus 2 or cosine x minus 2, that would just take it shifted up or down as normal. And if we were to add or subtract from the inside of the sine of the cosine wave, like say, for example, cosine parenthesis x plus 2, that would be a horizontal shift instead. And the reason I bring that up is horizontal shifts are called phase shifts in the graph. It's like normally the trigonometric function is thought to be in phase, but if you move it left and right, it changes the phase. So it can become out of phase with another wave. Which, if you're thinking about sound waves, waves which are in phase often are very harmonious or pleasantly sounding waves, if they're sound waves. And waves that are out of phase often have a less of a harmonious sound to it. Um, but anyways, I'm going to use all these terms as we're graphing functions, which is why it was so important to get into that. Now let us do a few examples. So going to the next page of the packet, it's there's just some assorted examples, and all of these there's a difference from sketching and graphing. Normally on an exam, I'm not going to necessarily make you graph the functions as I did on the previous page where we graphed every individual point, because that's very tedious, and I don't want to do that anymore. But what's important to note is they all have the same shape. Then if we're trying to do these sorts of examples, we just need to start with that base shape and apply those specific transformations to it. So it says find the amplitude and period and graph. And also we'll kind of note the equilibrium, each of the shifts and everything. But for example, let's say we wanted to graph -3 sine 2x. And another thing I wanted to mention is the implication here is that this 2x, both of these are within the trigonometric function. So it's not often going to be written. It's a common form of a way that it might be presented in a textbook. But this is the implication, is that this 2x is within the trigonometric function like that, even though the parentheses aren't written. And notice that in other cases, like say for example with this one, if it is x minus 3, the implication is that this -3 is not within the function. Usually it will be written like this. It's kind of poor notation, and if you're not really sure what will happen, sine only applies to what it's directly next to. And in the case of 2x, that's kind of what I'm getting at, is, well, is it just 2, or is it the 2 and the x which are in it? But this sort of writing usually implies that both are in there. But you got to be careful, because it is different whether it's on the inside or outside, because it will affect the transformation as whether it's horizontal or vertical. But anyways, in summary here, in this case, the number on the front is always going to affect the amplitude, which is, again, how tall it is. But remember, the amplitude is always the absolute value of that number, so will be +3 for example number 1. And then the number on the inside will affect the horizontal stretch or shrink, which in this case, I find it helpful to use the formula period is equal to 2 pi divided by k for sine and cosine, because the baseline period is 2 pi, and it will always be shrunk by a factor of that multiplier. So since it is 2, that would be 2 pi over k, which is just that 2 on the inside. And that would be 2 pi over 2, which is, of course, just equal to pi. So essentially, this wave will have a different period and a different amplitude than normal, and all that means is it's going to be shaped differently. It will still have the basic shape of sine. It will just, we have to make sure to apply all those transformations to it. And usually what I would start with as I'm trying to sketch it is start with a graph that looks like a trigonometric window. But basically, what I would always begin with is the period, because the period is the distance that it takes to complete one wave. So if, say, on this graph I was to graph pi over here, that's usually what I'm trying to graph, is one period of the curve. So what I could do is graph it all the way up to pi, because that's going to be when it's finished cycling. I could also say, well, what's the midpoint? But another thing to remember is that each trigonometric function is broken into those 4 key points, because it starts somewhere, goes up, down, back, and it will cycle through those in quarters, the quadrants of the unit circle. But it's not always going to be exactly those same numbers as the baseline graphs from here, because those were specific to untransformed waves in their normal form. But when they are transformed, it's all different. Anyways, but the period, that's a very key number. Amplitude is also key because it tells us, well, how tall is that going to be? What's going to be the height of that wave? So how should I label my y-axis? So in this case, 3 is the amplitude, so that's what I want to go up to. 3 is going to be the top. and also minus 3 is going to be the bottom because it has this equilibrium point. This one has not been transformed, it has not been translated up or down, so this one will still be right on 0, right along the equilibrium. But another thing is, notice the negative sign is something else we don't want to forget, because normally sine starts at 0, which is going to be the same case here, because if I were to plug in 0 into this equation, I would get y is equal to negative 3 sine of 0. Since the sine of 0 is still 0, and negative 3 times 0 is still 0, it's still going to start at 0. And you can always evaluate these with your calculator or point plot them in the same way we did last time, but the transformation principles make it so much easier to graph these. But basically, notice how since this one is negative, normally sine is going to go up like this, come back down, and do that. But this one's also different because of the negative sign. As we know, multiplying by a negative will reflect the graph across the x-axis, whereas multiplying a negative on the inside, recall, we'll flip it about the y-axis instead. Yes, I said that right. But my point is this one will actually be upside down as well. And basically, each one of those amendments to the normal sine wave, I'm trying to take them all into account so I can figure out what the final graph looks like. But this one's going to go down at the first of the 4 slats. It's going to hit its minimum point, the bottom of the amplitude. Then it's going to go back to equilibrium, go up to the top at this point, and finally it will end at pi. And each one of those points could be solved by, well, plugging in pi over 2 or pi over 4 or 3 pi over 2 into the original equation. And also, you can also graph these with your calculator. The issue with the calculator is that it will not give you the points, and it will give you a rough sketch of what's going on, but it might be hard to figure out the period and the amplitude and so on, because it's a calculator window. So let's just verify, because at this point I did a lot of stuff to try to figure out what does the graph of negative 3 sine 2x look like. But it's a quick way of checking to see, okay, did I mess this up at all? And in the same way that we graphed before, we can go into our y equals menu to graph the function. Let me clear off of everything else I had in there. So I can just type it in, negative 3 sine. Your calculator will always put the parentheses, which is important, and you don't necessarily need to close it off when it's at the end, but be careful to close it when it is important. But this should basically do exactly what I just did and graph the entire sine wave. And if we graph it in just a normal window, what we'll see is it looks quite a bit different than what I've got, because the normal window is typically going to be set from negative 10 to 10 and negative 10 to 10, which is not really that appropriate for a trigonometric graph. Another point I wanted to mention to you all here is that there is actually, your calculator has a trigonometric window programmed into it. If you go into Zoom, and if you look at number 7, notice it says Z-trig, which is like a standardized trigonometric window, which I wanted to show you what that looks like. It will actually decrease the amplitude. Notice that the range is now set from 0 to 4, just like the same graph that we were looking at when we were graphing cosine on the previous page, in a very similar way. One slight difference between that graph is that it actually goes from, this is just something that you wouldn't necessarily know unless I told you this, it's going to graph the x-axis domain is going to go from negative 2 pi to 2 pi. So it doesn't just do the right-hand side like we did with cosine and sine from 0 to 2 pi. It actually goes all the way from negative 2 pi to 2 pi. So notice that what I could also do is manually set my window to exactly this, which let's just do that. You can always just go into your window and adjust these things manually. But what I have is the domain is going from 0 to pi, so that's what I want my x min and x max to be. That will just graph the domain. And x scale, let's just not bother changing that. And then the y min and y max is going to be from negative 3 to 3, which is just my range. And if we graph that, it should graph one period, because that's what I figured out. I figured out the period, I figured out the amplitude, and this should graph everything perfectly assuming I did it all right. And notice we have exactly that. But there's a lot that goes into creating the graph and also working with our calculator to understand this wave a little bit better. In the next video, we'll do the rest of the examples. I'll speed it up a little bit, but key is figure out which trigonometric function are you graphing, and then apply each transformation to them properly.